Today we'll speak about normal varieties. It's part of, so I would do mostly geometrical part of the picture because otherwise it's hard to motivate. So let me tell you the motivation and explain a bit about normality, and then I would continue with the lectures. So suppose we have a, say, plane curve. For instance, it can be given by equation x3 is equal to y cube, y2. X cube is equal to y squared in C2. This curve can be parameterized. Namely, we have a parameter t such that t squared is x and t cube is y. And it's not hard to see that this parameterization is unique. It gives a one-to-one correspondence between the points x, y, which satisfy these equations, and points in C. So this curve, which is sort of clearly singular in 0, is in one-to-one correspondence with something which is non-singular. To see that it is singular, you can just check that. So you have the function t, which is square root of, say, x. And it's not, you can't express square root of x through this x and y. It's not hard to see that when you take, so it's the same, this ring of the ring of this of regular functions. So this curve is the same as a ring of polynomials on t squared and t third. And there is no t in this ring. So this means that this curve, singular one, well, you will see that it is singular when I define singularity, but it's clearly on the picture, it's sort of clear that it is singular, is not equivalent to a polynomial ring. I mean, its ring of functions is not equivalent to polynomial rings. This curve is not equivalent to the smooth, to a fine space. But it's one-to-one correspondence, and this correspondence can be given by polynomial functions. This is not good. And to avoid this, we need to well, there are many ways to avoiding this, because it's a problem which occurs all the time in algebraic geometry when you start with something which is smooth and you arrive at something which is singular, and you have to deal with singularities. And the first way of dealing with singularities is to do with normalizations and with normal spaces. Normality is a weaker form of regularity of non-singularities. So it's not hard, it's not obvious. In fact, it's even when we define smooth algebraic regular rings or smooth algebraic smooth affine varieties, it will be hard to see that they are normal, but it is true. Okay, so now I'm going to present a bit of background for what happens when you are interested in not in the ring of regular functions, but in the corresponding field of fractions of regular functions. What kind of geometry we obtain when we restrict ourselves to the field of fractions instead of the ring of regular functions. The geometry which is obtained this way is called birational geometry. It's a geometry of affine varieties up to equivalents, which we call affine varieties equivalent if they have the same ring for fields of fractions. Okay. This is slightly related to normalization, so I would do it together. Okay, the first definition is something that probably the first step in algebraic geometry is the idea belongs to Zariski and was popularized by Grothendieck. You can define topology on points associated with algebraic varieties, even if you don't know any topology, you don't have your field is not C, but some finite field or periodic field, some bizarre, strange field. But still you have some topology. It's called Zariski topology. It's very strange, but it's useful. So definition, suppose you have I inside OA, X an ideal, and OX a ring of regular functions. You have the set spec of OX, which is our X, and the Zariski closed set is a set of zeros of I. So for each ideal, you have Zariski closed set, and the Zariski closed sets are in one-to-one correspondence with the ideals. It's sort of clear that infinite intersection of this kind of sets is again Zariski closed. This corresponds to having infinite. Yeah, and the same with the unions. If you have so intersection corresponds to unions of two sums of ideals, and intersection corresponds to intersection of ideals, of course. So if X intersects with Y, no, it corresponds to union IX. You take just plus to IY. And again, as usual, if you have finite union of closed sets like x1 dot xn, then you have corresponding ideals ix1 dot ixn, and you take the product ix1 times ix2 times and so on times ixn. In other words, you take functions which belong to the first, to the second, to the and so on ideals, and you multiply them all, and you obtain functions which vanish on all this x. So the corresponding ideal will be ideal of the union. So finite unions of algebraic sets and infinite intersection of algebraic sets are algebraic, and the Zariski closed sets are just algebraic sets of the algebraic variety, affine varieties. Okay, so example. So a subset of C is Zariski closed if S inside C, S is the whole C, or S is finite. So if you have a finite set, it's a zero set of certain polynomial. Just you take the polynomial product of T minus AI, where AI run through your finite set. And if it's the whole C, it's just trivial It's also Zariski closed. It's algebraic. So, okay, so yeah, the corresponding topology is also known as cofinite because open sets are complement of finite sets or empty. So this is a simple topology which you can define even without any ideals or algebraic geometry, but for bigger dimensions, of course, won't work. You need the closed sets will be your curves, so you can actually reconstruct more or less the algebraic structure from the Zariski topology for dimension 2 or bigger. Of course, Zariski topology is not Hausdorff, clearly, because you have finite sets, complement of finite sets, they intersect. Intersection is non-empty. So if you have two open sets in Zariski topology, which are non-empty, the intersection is non-empty. It's very, very non-Hausdorff. Okay, this is a picture of Zariski, who was one of the founders of algebraic geometry. He was a teacher of Hironaka, Mumford, well, Abyankar, lots of famous people. I think he has probably Nash, maybe. Well, he got world records for field medalists as students. Okay, so the Zariski topology is mostly due to Grothendieck, who defined it, who used different spectra. This is something important. I would, what I'm doing is slightly misleading, because when I say spectrum, I mean the algebraic variety, and in fact its points are maximal ideals. However, if you do what Grothendieck suggested, you don't restrict yourself with maximal ideals. You do also prime ideals. So the usual spectrum, not the one which I defined, but the classical algebraic geometry spectrum, is a set of all prime ideals. I won't use this, but it's important. Okay. Then Zariski topology. Again, if you have Zariski closed sets correspond to ideals. If you have an ideal I, you consider the set of course, here it's written contained. It should be opposite. I'm sorry. So Zariski topology, if you have I inside R, you consider the set of all P which contain I. This is ZI. It's a subset. So the P is prime ideals. This is Zariski closed, and this is the set of all closed subsets of this set of all prime ideals. Okay. So it's the same if you forget. So maximal ideals are in what we did is just points in algebra in algebraic in a fine variety in algebraic set. So if you this is the same topology, except that we now consider all prime ideals, which sometimes is better, but it's better if you do lots of algebraic geometry. We're not going to. So why do you want prime ideals? It's very simple. it's an important, thank you for asking this. So consider a map of homomorphism of ring, A to B. So generally speaking, a preimage of a of a maximum ideal is not maximum, it's prime. It's not hard to see that. And we want it to be, of course, we want it to be functorial. So for general rings, not for our case, when you can really have map from maximal ideals to maximal ideals, for general rings, you have the corresponding map from spec of B. You want to define a corresponding map from spec of B to spec of A. And it won't work with maximal ideals. You need prime ideals to, you need prime ideals to work it well, because preimage of maximum can be prime. Lots of examples. So it's really better if you do abstract algebraic geometry in general setup to work with prime ideals. Maximal ideals just don't make sense in that context, unfortunately. But for us, of course, points are points. Maximal ideals are maximal ideals. They're the same as points, and we have maps on points associated to any algebraic map, because you can write it explicitly in terms of coordinates. So there's no problem if you do it over C and don't go to some other more complicated things. Okay. Now I'm going to start a bit about these birational maps. The first thing you should have to do, you have to define dominant maps. So definition. F from X to Y, a regular map. So it's algebraic morphism. Dominant if the image of F is Zariski dense, so it doesn't contain any non-trivial closed subvariety. In other words, there's no proper closed Zariski subvariety of Y which contains image of F. This is the, in other words, that is a Zariski closure of f of X is Y. It's not hard to find examples of that, counterexamples. All surjective maps are clearly dominant, but not only. Let me give you another example. For instance, you can take X, C example, which is slightly less trivial than what you can think. C without a point maps to C. So we already know what is Zariski closed subsets of C, and this is clearly not, doesn't contain the image of that. So this is, and how this map looks like on the level of rings, this is not hard to see, because here the corresponding ring is just polynomials. And this is Laurent polynomials, because you invert, removing a point corresponds to inverting a T, so it's C of T and T minus 1. And this is an embedding map. And this is, of course, the same as C of xy quotient by xy equal 1. As usual, this is just localization of C of t by t. Okay, so this is an embedding of rings, and this is surjection of the corresponding algebraic varieties. And of course, you can represent this geometrically, because xy equal 1 is just hyperbola. So this is your algebraic variety, C without 0. You can think of it as hyperbola, and they project it to the horizontal line by forgetting, say, one of the prime, by forgetting y. This gives you a projection to this from hyperbola to C, which to a line which corresponds to embedding of the regular functions on a line to regular functions on this hyperbola, which is Laurent polynomials. Okay. So now proposition, it's a characterization of dominant maps in terms of what happens with the functions. Proposition. We have a morphism of fine varieties. And so F is dominant. F is dominant if and only if F star, the pullback of regular functions from OY to OX. This is pullback. F star is injective. Okay. So let's prove it. It's almost trivial, in fact. So we need to do it both directions. So suppose that step 1, suppose that F star is not injective. You need to deduce that F is not dominant, so you have I inside, it's an ideal in OY. It's a kernel of, so I is a kernel of F star. And then all points x in X mapped to the zero set, of this ideal, because if you have a function which belongs to this ideal, then its image in OX vanishes. So this means that every function, if you have a point in OX, its image in and you want to evaluate a function from OY on this point. If this function was in this ideal, it will vanish on this on the image of this point. This means that X is mapped to the annihilator, to the zero set of this I. So this cannot be, it belongs to the Zariski closure is this annihilator of I, which is non-trivial because it's a non-trivial ideal. So this is one direction. If you have 0, then this 0 set contains the image of x. Okay, so conversely, so step 2, suppose that f of x is contained in I. I want to say, then I want to imply that f is not dominant. So you have yeah, if you have a function f which belongs to this ideal I, this would immediately imply that oh, sorry, they have f here already. Let's call it mu. This would imply that so if f of x belongs to the set z, which is not equal to y, it's a proper closed subset, and I is ideal of z, then f of x belongs to z. This implies that any element mu inside I vanishes on f of x, and this implies that f star of mu is equal to 0. So if the map is non-dominant, this implies that the map, if f is not dominant, f star has zeros. So if f is not dominant, then f star, kernel of f star is non-zero. And this is step 2. And step 1 says conversely that if the kernel if this is non-zero, then it is non-dominant. So this is step 2. This is step 1. Was I clear? Completely? So the first step says that, okay, suppose it's not injective. So we start with this. You have kernel of f star. You take the ideal, which is a kernel is ideal. So you have I, this is your kernel of f star. And for each x, for each point x in the first, affine variety x, it's mapped to annihilator of I, because it will vanish in x, in the image of x. So any function which belongs to I would vanish in the image of x.
Because it's the kernel, it's not
Yeah. Yeah, because it's the kernel of f star. Which implies that your map takes x to this common zero set of I. So it's really tautology, but somehow it takes some effort to access. So is it okay now? Thanks. Okay. Now I would repeat more or less the same, but in slightly different terms, namely in terms of field of fractions. So we already had this notion of localization. And field of fraction is like localization, but with respect to all elements of of your ring. So first, let's repeat what is localization. So you take, suppose you have S inside R. S is multiplicatively closed, which means that for all x and y inside S, x, y belongs to S. And we can define localization of R in S, which is sometimes denoted R of S minus 1, and sometimes denoted by R, and then you have S in brackets. This is square brackets, and this is round parentheses, round brackets. Okay, so what it is, it's a set of all fractions, formal fractions. So R of S minus 1 is set of formal fractions. A divided by S, where S belongs to. Yeah, of course. If it has 0, then it just, everything breaks. It just, you obtain 0 ring, which makes very little sense. So, yeah, thank you very much. So you have formal fractions. Of course, I already gave explanation last time how to produce formal fractions by adding an extra variable to your set of variables defining the ring. So you just add a variable, say, ts, such that sts is equal to 1, and you take your ring, or R of ts, the polynomial ring quotient by the ideal generated by ts minus 1. This is the same as adding this formal variable, but instead you can just formally add them, and you define additional multiplication on this kind of fractions by saying a divided by s multiplied by a1 divided by s1 is equal a1 divided by s1, and then a divided by s plus a1 divided by s1 is equal to a s1 plus s a1s divided by s1, and this is the way how people learn how to add and multiply fractions in grade school. So it's very basic, and we just repeat something from the grade school in formal variables. So anybody who did rational numbers from integers already knows this procedure. But it makes sense in this big generality. What is important is typically the fractions are not finitely generated because your set S can be arbitrarily big. Okay, now field of fractions is just when you take all definition. Suppose you have R is ring without Z divisors. Define a ring of fractions. It's usually, well, it's often denoted fractions. K of R. Here's not, I did use the definition, but it's often, is localization of R in R without 0. So you localize your ring for over all the all non-zero elements. You invert all non-zero elements. So this is how you obtain rational numbers from integers. Okay. Now claim. Suppose you have f from x to y, dominant, and moreover, x is reducible. X is irreducible. Then y is irreducible. Also irreducible. Irreducible. And yeah, and f star from OY to OX can be extended to fields of functions. There's essentially nothing to prove. Well, except that what is clear is that this is injective map. This is something we have already did, and because it's dominant. And this is injective map of rings without zero divisors, except that we didn't prove that OY has no zero divisors. We proved it's given only for OX. So essentially the only thing we need is to prove that OY has no zero divisors. OY has no zero divisors. Zero divisors because OY is embedded into OX. This is because of dominancy. This is something I explained a few minutes ago, that every dominant map induces you embedding of rings. And OX has no zero divisors. So this implies in particular that y is irreducible. And then it also implies that this embedding is an embedding of rings without zero divisors. And you can localize over y, and then you just map a fraction to a fraction. Like f, the corresponding map f star from the ring of fractions of k of y. This is the field of fractions on y is mapped to field of fractions on x by taking x f of a quotient by b is equal to f of a quotient by f of quotient by b. And then we check that these equations which define you the multiplicative and additive structure on the fractions are compatible with these maps, which is clear by definition. So we need to define this map. We do it formally without any problem because the formal definition of fraction field is compatible with this kind of homomorphisms. Clear?
Typically it's not subjective,
Typically, it's not subjective,
for example.
yeah. So they,
It's obvious, yeah, I see it.
yeah. But it is injective, so at least you have one part of the. Okay. So what does divisor mean in algebraic geometry? It means a subvariety of codimension 1. We didn't define dimension. In fact, you define dimension using the notion of a divisor. But the intuition is like that. Now, principal divisor is like principal ideal. So generally, divisors should be defined by one. They correspond to ideals which should be defined by one element. Unfortunately, it's not entirely true, because you might have divisors which are not divided by. So principal divisors are a variety corresponding to ideals which are principal generated by one element. So definition. Suppose that you have a subvariety in, well, you have a regular function. F inside OX is regular function. Well, we want it to be really a divisor. If you have several components, we want them to be divisor in each component, so we want it to be non-zero. So F is non-zero on all, yeah, so let's do it like that. F restricted to xi is non-zero for all irreducible components, for all components of x. So you have irreducible components, which are your xi. This doesn't mean that it has no zeros. No, it might have zeros, but it shouldn't be zero on the whole component. It should have a point on this component where it is non-zero. Then the zero set then the zero set of F is called principal divisor. Or complete intersection divisor. And all irreducible components, let's call this zero set D of D are called divisors. In other words, divisor is something you can obtain as an irreducible component of a zero set of a function. Sometimes it happens that all divisors are principal. This is more or less the same as principal ideal ring, and we shall explore that a lot because it's important, and you will see. Okay. So now, yeah, first we can remove divisor. At least you can remove principal divisor. So if
So the principal divisor is just a unit.
zero set of a function. So remark the first observation why it's a good notion. So if you have z inside x is a principal divisor, then x without z is a fine variety. With a ring, with a structure ring, so let's call it x1. Ox1 is equal to O of x, where we localize by f minus 1, where f is a zero set. Well, better to say that z is zero set of f. In other words, we can also rewrite it as so here it's d instead of z, so let's call this d here and d there. O of x without d is O of x, and you add a variable, and you take a quotient by the ideal T f is equal 1, where f is, so d is zero set of f. Yeah, it's localization. It's the same as Ox of f minus 1. So it's sort of, to see that, you can just again look at this picture with hyperbola. You project hyperbola to a line, you obtain hyperbola without the line without zero. In other words, if you have a point which corresponds to maximal ideal which doesn't belong to zeros of D, then it would give you a point in the the maximal ideals. This is something we have already discussed, I think, several times. So the maximal ideals in O of x, where you invert f, is spec of Ox without zero set of D. Of f. So first, the ideals of this ring are embedded into ideals of O of x. This is something we had already. And then you can easily see that if you have an ideal which doesn't contain f, then the localization is a non-trivial ring, so it gives you an ideal in that. If you have maximal ideal in Ox which doesn't contain f, it gives you a maximal ideal in Ox of f minus 1 in the localization and vice versa. So it's 1-to-1. Okay. Now we're interested in morphisms which induce equivalence of fraction rings. So definition, they're called birational. A morphism of affine varieties is called birational if it induces an isomorphism on fraction fields. Well, for that to make sense, of course, you want your morphism to be dominant, so I would add dominant. Because for non-dominant morphisms, we have no map on fraction fields. It makes sense only when the morphism is dominant. Okay, and we have this example which we just discussed now. So example, x without d is mapped to d. Oh, to x. And of course, the fraction field of that is the same as fraction field of that, because the O of x without d is just localization of x, of O of x. So the corresponding fraction fields are the same. Okay. Maybe it's a good time to have a break. Yeah. So can I have a break for 5 minutes? Okay, let me continue. So I ended up with explaining what is birational morphism. It's a morphism which induces equivalence on fraction fields. So now the main result about birational morphism is that it is in fact an isomorphism outside of certain closed set. So theorem, let f from x to y be birational map, morphism of affine varieties. So in particular, it is the corresponding grids are finally generated. If they are not, then what I'm saying won't be true. But it's already varieties. So then there exists a divisor, principal divisor, So we'll have to take a divisor in Y and its preimage, which is denoted by Z inside Y. And this gives you a map, f from x without preimage of y of Z to y without Z, such that this map is an isomorphism. The converse is very clear, is very simple, because, okay, this is an isomorphism, but the ring of the fields of fractions on that are the same as the ring fields of fractions on Y by this lemma, which was somewhere here, by this example. And the field of fractions of this variety is the same as field of fractions on X. So if you have an isomorphism between these varieties, this gives you an isomorphism of fields of fractions from X to Y. So the converse is clear, but this direction is less clear. So let's prove it. So the idea is that if you have a birational morphism, it does something bad, but the set where it does something bad, it might glue some points and might glue some subvarieties together, do something unpleasant. But the set where it does something unpleasant is Zariski closed. You can remove it by removing the divisor where it is contained. And then it will be, your birational map will be an isomorphism. Okay. So the ring OX is finitely generated. OX is finitely generated. So you have a, so this map from OX to OY is already injective. If it were surjective, we would be done. So we need only to remove divisors in such a way that this corresponding map from O of Y without Z to O of X without F minus 1 of Z, we want this map to be surjective because it's injective for free. It's injective because it is dominant. Okay, so, but it's finitely generated. So we need to do it by step by step by adding the generators. So you have x1.xn generators. And for each of these generators, you can add xi is equal to y1 divided by y2, where y1, y2 belongs to oy. This is because on fraction field, this corresponding map is an isomorphism, so each xi belongs to the ring of fractions of oy. Okay, now I claim that for there exists f inside oy, such that for all a inside ox, there exists b inside oy, such that a is b divided by f power n for some n. Okay. Indeed, each xi, this is our generators, are written as yi divided by, what is notation I used here? Yi prime divided by f. Well, yi divided by something, yi divided by fi. Here in the slides I use f for embedding, but it's in fact, we can consider this embedding map as just we're going to identify f with its image and forget about the embedding. So xi is yi divided by fi, but this is the same as xi is yi prime divided by f, where yi prime is yi multiplied by f, product of all f, j not equal to I, and f is a product of all fi. We just multiply the first term by the product of all the rest of fi, and then you multiply the bottom term, the denominator, by the product of the same, and it will give you a product of all fi. So we have x is expressed as a quotient by f, and then since all since all elements of O x are polynomials on xi, and this is the same as yi divided by f power n, y prime. This implies that all elements a inside Ox are some polynomials of yi prime divided by f in some very big power. And this implies, in turn, that O y with f localized is the same as Ox with f localized. Okay, good. Now we can remove the divisor corresponding to f. So this is the ring. This is the same as O of y without zero set of f. And this is the same as O of x without annihilator of f. Again, or the image of f. Doesn't matter. What is, yeah, so here we have probably write f minus 1 for that to make sense. Okay, so this is our divisor. Our divisor is just an annihilator of these functions, which are just product of all denominators for all generators of the variables generating x. Okay, so this is how birational maps works. So you just remove divisors and they become an isomorphisms, which is convenient. That this is something we shall use. Everybody uses a lot because it's quite often that you can have to pass from the ring to its fraction field to work with algebraic geometry or commutative algebra of this thing. Okay. So I finished with birational maps. Now I'm doing with integral dependence. This is very simple, similar to what we had when we discussed Noetherian models, with a twist, because the twist is that we have two kinds of finite generatedness, and this is the second kind of finite generatedness, not identical to the first kind. Let me explain. So definition. So you have A inside B ring. So B is integral over A if B is finitely generated as a model. Well, it's here the definition is slightly different. So let's, before I'm doing it, let's say that B inside B is integral over A if the corresponding, if the ring A, where you added 1, B, B square, B, and so on, is finitely generated as a model. So this is also denoted as A of B. The second definition is Monique polynomial. We had it last time, but last time it was not, in fact, used. Monique polynomials are polynomials with leading coefficient 1. P of t equal to t power n plus a1 t power n minus 1 plus and so on. That is with leading coefficient. This is the leading coefficient, the coefficient with Tn. Okay. So, claim, which is quite trivial. If you have B inside B, which contains A, is an integral if and only if B is a root of Monique polynomial with coefficients in A. Okay, if you have a relation b power n is equal to this sum, a n minus t or I t power I from I equal 1 to 0 to n minus 1, b should be b power I. This is the relation which I wrote here.
Probably I plus 1.
I think here we have a1 t n minus 1. So
Then you have a
n minus I b power I, and from 0 to n minus 1. I just rewrote this to here. And this implies that then you have the same relation for bn plus 1, and so on and so forth. So this model is the model A of B is finally generated as a model. Of course, it's finally generated as a ring. But here, finally generatedness means for models. It's entirely different finite generatedness. Okay, so this is one direction. If it is a root of Monique polynomial, then it is integral. This is integrality of B by this definition. Conversely, if A of B is integral, this means that B power, well, you add more and more relations. At some point, it stabilizes. So at some point, B power n will belong to a sub-model generated by 1, B, and so on, B n minus 1. Because this sequence stabilizes. It's finally, we don't use notarianity, but it still stabilizes because by definition, it has to stabilize. Otherwise, it will be infinitely generated. Okay, so this means that Bn is equal to sum from I equal 1 to n minus 1, again of a n minus I, b power I. So it is a sum of smaller element with coefficients in A, again I n minus I. Here we have n minus I in the bottom, of course. And the coefficients belong to A. Okay. So finite generatedness implies existence of Monique polynomial. Monique polynomial implies existence of finite generatedness. So both sides of this claim are proven. Both equivalents. This is equivalent conditions. Okay, the corollary, which is trivial. B inside B is integral over A if and only if B is a root of Monique polynomial. Polynomial P of t inside A of t. This is a bit like integer counterpart for Galois type of results we discussed last time. They're very much related. So in number theory, you consider this kind of dependence every, like wherever you go, you consider this kind of dependence. Now we have, it's the same kind of results that we had last time and several times before. For addition of algebraic numbers and multiplication, they are also so sum and product of two algebraic is algebraic. This is something we know. The same is true for integral. So claim if x and y inside B are integral, so B contains A. over a, then x plus y and xy are also integral. Of course, this is no longer true for fractions. Fractions are typically non-integral. I mean, integral for integer numbers, integral is just integral. If you have a, well, you will see. So fractions are never integral. Oh, typically non-integral, even for very good rings. Okay, so proof. Yeah, it's so you have x and y integral. This means that y is integral over a of x. This is because y is a root of monic polynomial of coefficients in a, but then it is a monic polynomial of coefficients in this bigger ring. It's the same. So this implies that the ring of polynomials from, the ring generated by x and y is finally generated as a model. Because this ring is already finally generated as a model, and then you add one more element, and you can, if you have, so if a of x is generated by 1 x dot x power n minus 1, and a of y is generated by 1 of y dot y m minus 1, then a of these two elements added is generated by 1 x y x y x square y, and so on and so forth, up to x n minus 1 y m minus 1. So you have all these pairwise products of powers. So the first collection generates you the ring a of x, and the second collection generates you the ring a of x and y, and then you can just decompose any element for this onto a sum of this. First, you decompose it to a sum of different degrees of y with coefficients in a of x, and then you decompose these coefficients onto powers of x. This is also an exercise to prove it in bigger generality. If x is integral over a, y integral over a of x, prove that y is integral over a. This is the same argument. So you probably should do this exercise at some point. This notion is very important. It's more important in number theory than in algebraic geometry. But number theory uses algebraic geometry and it uses commutative algebra, so this is very natural. So what happens is that typically you take a ring of integers in some arithmetic field, which is a finite extension of, so you have z inside k, which is finite over q. And then you have OK, which is a ring integral closure of z in k. And this is the point where all number theory starts. because number theory is algebra or geometry or commutative algebra of this ring. So this is a really important notion which I'm going to define now. Definition. So suppose you have a ring A inside B. Then consider a set of all elements. So let's A1 inside B be the set of all elements of B which are closed, which are integer, are integral, over A. This is subring as we just discussed. So then A1 is called integral closure of A. Is called integral closure of A. And A is called integrally closed when it is integrally closed in its fraction field. So A is called normal or integrally closed if A is integrally closed in K of A fraction field. Okay, so integral closure is a ring. It's something we have discussed. And of course, now we can define normal affine varieties. It will be affine varieties with integrally closed ring of regular functions. Suppose you have X affine variety. Is called integrally closed or normal if its ring of regular functions is integrally closed. Or normal. Okay. So equivalently, so remark. This is equivalent to having all finite birational maps x1 to x isomorphic, being isomorphic. Why it is so? Well, if you have a finite birational map, it's obtained by adding, so if you have x1 to x finite birational, finite means that, I think I gave this definition last time. No. It's x1 is finite if O x1 is finitely generated as O x model. Okay, now you have OX1, but the fraction field is the same. It sits in in fraction field of OX. And it's finite over OX. It's finally generated over X. So it belongs to the integral closure, because all elements of this ring are roots of monic polynomials. So they belong to integral closure. Integral closure is by definition just collection of all things which are roots of monic polynomials inside inside the field of fractions. Okay, so it should be this. All regular functions on X should actually belong to on OX1 should belong to OX. So the corresponding map from OX to OX1 should be actually an equivalence. So this is one direction. On the other hand, if it's so this means that if you if this is normal, there are no such maps. But if there are no such maps, then if you add an element which is finite, which is integral over OX to OX, the corresponding finally generated ring will coincide with OX. So this means that this element in the ring of fractions which actually belong to X. So this is really an equivalence. So next time we'll define normalization, which is the biggest possible the biggest possible finite birational map from something to X. So it will be like initial object in the category of all finite birational maps from something to X. And this is a very nice notion. Of course, it's not hard to define. Okay, before I do it, let me give an example of something normal, and then I probably stop. So, fractional ring, factorial ring. This is something we had already, and you had some handouts about this, where I tried to explain that the rings such as integers and the polynomials are factorial. This means that they have unique prime decomposition. So definition, if you have P inside R, is called prime, is prime if for all P1, P2 inside R, such that P1, P2 is divides P. This means that they, so this is the by definition, this is equivalent to P1, P2, to them belonging to the ideal generated by P. This is symbol of division. Yeah, so here it's actually a different definition. I'm sorry. Well, I will give this definition because I think that one is wrong. But please check Wikipedia; they have it. Is prime for all P1, P2 such that they divide P, P1 divide P, or P2 divide P. What I infer is that this is equivalent. So P is prime if and only if P, the corresponding ideal is prime. And what is written here is not prime, it's non-decomposable. Sorry about this. It's an error. So this or, so it's P1 or P2 belong to P. This is the same as p bin, ideal generated by p bin prime. Of course, this implies non-decomposability. This implies that pi can be decomposed onto a product of things which are not invertible. But this is good notion. Okay, so definition, anyway, are, so for factorial, this of course equivalence. So R is factorial, so this makes it, the distinction senseless if you work with factorial rings. S is factorial if all elements of R are decomposed to a product of primes product of pi power alpha I of primes, and this decomposition is unique up to permutation and invertible multiplier. In integers, only -1 is invertible, so this means that you can write primes, but you can switch pi by and minus pi freely as long as the product works. So these factorial rings. Just the rings like integers or polynomials which have unique prime decomposition which is unique up to a permutation. Okay. So now you have factorial ring, then it's integrally closed. Proposition. Let A be factorial then A is integrally closed. So there's an example from elementary number theory of when it really works. You can consider the field Q of square root of -3. This is not, it doesn't have prime decomposition because you have 1 plus square root of -3 multiplied by 1 minus square root of -3 is 4, is 2 by 2. This is two prime decomposition of 4s, which are clearly non-equivalent in this ring. The point is that it is not, in fact, integrally closed. So if you add 1 minus plus square of -3 by 2, it becomes integrally closed. And this is a root of something like, do you remember? Something like x squared plus x plus 1 equals 0. Something like that.
Be -5 under the roots.
-5?
Not here, but the ring Q of the square root of.
No, 3. Yeah. Yeah, because it's in fact it's a root of, it's a third power root of unity, I think. or minus 1. So we have something like that because it's, yeah. So this is a very basic example which Euler already noticed, that if you try, he was trying to prove the Fermat big conjecture for the exponent of 3. So he wanted to prove that x3 plus y3 is never equal to z3, unless there are zeros and ones. And he came to this field, which he wanted he wanted this field to be, I think he assumed that it is, he didn't even notice that it is not integrally closed, because he probably meant to say, he was writing about this field, but he thought about this field. Or maybe he noticed that, I forgot. But then, yeah, then it was, then he proved, it's not hard. In fact, it is, I think, in the handouts that this field Q of this root is in fact integrally closed. I think we have it in handouts. And if we don't, you can prove it. It's not hard. And then this implies Fermat for exponent of 3. And then, of course, this is the starting point for all 19th century number theory, because then we realize that you can, if you're lucky enough and you have a number field, a number ring, which has prime decomposition, you can prove Fermat for appropriate exponent. And then it was Sophie Germain who defined Germain numbers, which are prime numbers such that the root of unity of order P generates a ring with which is factorial. But then it was, people realized that these primes are very rare, so she proved it. She proved Fermat, but for very little number of primes. For small primes, it's okay. She actually proved it for like lots of primes before 100, but then after this Sophie Germain primes gets more and more rare to the point where they almost don't exist. But still, this observation that you have to do something with your field so that it becomes factorial was important, and this proposition is a special case of this funny, well, more general case of this number theoretic research. Okay, so let's prove it. It's elementary. So step 1. Step 1. You have u divided by v is the root of Monique polynomial. So you have u divided by v power n is equal to sum a n minus I u by v power I from I equals 0 to n minus 1. You multiply everything by v, and you obtain that u power n is divisible by v. Because everything here, you have here the exponents which are smaller than n. So if you multiply it by v power n, this becomes u power n, and this becomes divisible by v. And since we have everything is factorial, this implies that u is divisible by v. Well, let's start with u and v coprime for simplicity. Then you have u divisible by v by the uniqueness of the prime decomposition. And since they are coprime, and which is this impossible, so v is invertible. And then this implies that if you have a root of Monique polynomial, then v is it's actually integer. Then u v is u by v belongs to your ring A. This means precisely that it's integral closed. Then A is integrally closed. So the integral closeness for factorial rings is one-line argument. There's nothing to do. Okay. So now I can give an example, and that's it. Well, yeah. So let me give you an example of integrally closed something. So example of normal. So C of t is factorial. This is something we hadn't had doubts. Then the corresponding algebraic variety, which is just C, is integrally closed. The affine line. Sorry, it's normal. And another example is due to Gauss. Gauss proved that the polynomial rings are integrally closed. Oh, sorry, factorial. So Gauss. So P is something we'll discuss next lecture. P1 dot. So you have polynomial rings are factorial. Then the Cn affine space is normal again. Okay. I'm done. Thank you very much. Muito obrigado. Eu termino.